All right. So I will talk mainly about the application of antiferromagnets in terahertz frequency signal processing. This talk will not contain a lot of new physics. This will be a talk of how to design useful devices in terahertz frequency region from a theoretical point of view. I will talk a little bit about difference between antiferromagnetic materials and ferromagnetic materials and how the antiferromagnets can be used in terahertz spintronics. I will talk briefly about oscillators based on antiferromagnets and a little more detail about detectors. I will talk about the construction of a resonant antiferromagnetic detector of terahertz frequencies. And then I will discuss the tunability of receivers, how you can make these receivers of terahertz frequencies tunable. Before I talk about the motivation, I would like to say that Neel, who basically discovered antiferromagnets and studied them in detail, in his Nobel Prize address said, "These are very interesting materials, but absolutely useless." I will try to prove that it is not exactly that way, although making use of them is not a trivial issue. So first of all, we will be interested in a frequency range of about 10 to the 12 hertz, and it is rather easy to generate everything lower and many frequencies higher than that. But there are practically no natural resonators having resonance frequencies in the terahertz frequency region. And the antiferromagnets are almost the only class of substances which have natural resonance frequencies lying in a terahertz region. What's the difference between dynamics in ferromagnets and antiferromagnets? Well, ferromagnets, they have magnetization, order parameter, and the resonance frequency of a ferromagnetic resonance is proportional to the external field and the dipolar fields, which to a certain extent these dipolar fields can add also the anisotropy fields, and dipolar fields are also almost totally dependent on the shape of the sample. These are demagnetization. And you see that the external field realistically cannot be more than half a Tesla for any portable device. So the frequencies which you can reach are limited by, say, 20 or 30 gigahertz. So if you want to do something which is higher than that with ferromagnets, you need either huge magnets or there is no way. In the antiferromagnetic substance, there are two sublattices which are oriented antiparallel to each other. The field which keeps them antiparallel, this is the internal uniform exchange field or Weiss field, the field which is responsible for ferromagnetic order. This field is about 1,000 Tesla. So trying to interact with this field is almost useless. How big field you can create? 10 Tesla, 20 Tesla, not 1,000. So in some antiferromagnets, you can study statics by changing the external field, and chances to change the dynamics using external field are almost nil. But the antiferromagnetic resonance frequency is determined by the product of this exchange field, internal exchange field, and rather small anisotropy field. And that means that you can influence the frequency of antiferromagnetic resonance mainly by changing the anisotropy field of the crystal. Now, if we want to actually create a generator, we need to somehow excite this eigenmode either in ferromagnet or in antiferromagnet. In a ferromagnet, you can do the following thing. You can actually create the spin polarized current where the vector of polarization will be parallel to the magnetization, and that will create, with a certain direction of the polarization, will create an anti-damping torque, which will try to destabilize the static direction of magnetization, which is actually, in a static case, simply parallel to the external field. If you will try to do something like that in antiferromagnet, we have two directions of magnetization, one sublattice and the other one. And so if you destabilize one of them, you will actually stabilize the other one. So if you apply the external spin torque or spin polarization, which is parallel to the direction of magnetization, in this case to the direction of these two magnetizations, the net result will be zero. You will not be able to excite anything. So there is no chance to actually excite the eigenfrequency. So if you want to excite something, you need to do something else. And what can you do? You can apply the spin polarization perpendicular to the direction of magnetizations in the antiferromagnet. Perpendicular, in that case, what you can do, you can slightly tilt the antiparallel directions of magnetization. Can you tilt it strongly? No, because you see the force which makes them antiparallels 10,000 Tesla. So you can probably get tilt of 1 degree or a couple of degrees. But this is enough. If you do that, the tilted antiferromagnetic sublattices will start to rotate in this huge exchange field. And if you will do that, you will get the rotation of this magnetization order in the huge exchange field, and you will get frequencies of this rotation, Larmor frequencies, which are in sub-terahertz or terahertz frequency range. Now the question is how to choose the crystal. And there are plenty of uniaxial antiferromagnets, and among them there are dielectrics, and there are semiconductors, and there are conducting materials. And there are also plenty of bi-axial crystals where the anisotropy is more complicated. So the frequencies, the characteristic frequencies of antiferromagnetic resonance, you see range from 1 terahertz to say 160 gigahertz. And this is a hematite where the frequency is relatively low. So it is a kind of a proof of principle material, which is a antiferromagnet, but the frequency is still rather low. So you can use almost a conventional electronics to do experiments with. It was shown experimentally that if you put an antiferromagnet in contact with a ferromagnetic material and you excite a ferromagnetic resonance in the antiferromagnet, in the ferromagnetic materials, there will be a spin pumping into the antiferromagnet, and you, using inverse spin Hall effect, you can actually detect the signal. And that was demonstrated both in chromium oxide, in manganite fluoride, and in hematite. So there is a chance to receive the external signal using the antiferromagnet, and the response will be resonant. And if we find a way to tune this resonance also, then we will get both a generator and a receiver which is continuously tunable in frequency. So our goal, basically in this talk I will talk about only receivers, to create a tunable resonant receiver of sub-terahertz signals based on antiferromagnet, to find how it can be tuned, and to find how we can get the output of this material, and how can we excite the signal in this resonator. This slide simply summarizes our theoretical project of how to create a generator. And a generator can be created by putting a layer of antiferromagnet on a platinum electrode, and then the current flowing in the platinum creates a spin Hall effect, which creates a spin torque on the boundary. So the antiferromagnet should be very thin. And in that case, there will be a tilt of sublattices and rotation of sublattices in the plane perpendicular to the hard axis of the material. And the equation which describes this is very similar to the equation describing the oscillations in the Josephson junction, where this one over exchange field plays the role of the effective mass. The effective damping is usual Gilbertdamping, and the Josephson potential is replaced by the potential where phi is the azimuthal angle of rotation, and of the sublattices. And the frequency, as you see, can be about half a terahertz when the current density is about 10 to the 8 ampere per square centimeter. And we have here a big specialist in spin torque oscillators as our chair, and he knows that in principle you can reach these current densities in real experiments. Now the receiver. We will try to use the receiver using a very similar device. The device consisting of the antiferromagnetic layer, a layer of platinum or any other heavy metal, where we will supply the AC signal, which is the signal which we are going to receive, plus a DC signal, which I will show can help us to change the resonance frequency in the antiferromagnetic material. And the top layer will actually receive the signal obtained due to the magnetization dynamics in antiferromagnet using the inverse spin Hall effect. I will not discuss these equations in detail. I will simply say that this is the equation for the Neel vector, or order parameter of antiferromagnet, which is basically difference between magnetizations of sublattices. This term is the inertial term, where this is the effective mass. This is a damping term. This is a term describing the anisotropy of material, and we will have two spin torque terms, one related to the DC current which we are supplying to move the frequency, and AC current, which is our actual signal. If you do first of all the static problem, you will see that DC current basically changes the direction of the Neel vector. And this angle is proportional to the current, and that way you change the frequency of the antiferromagnetic resonance. While the dynamic term, AC term, basically gives us the high frequency response. And this high frequency response looks like this. This is a normal resonance curve. As you see there, for the material which we're using here, which is, I think, iridium manganate, the frequency is about 450 gigahertz. Line width is about 60 gigahertz. And although this Q factor is only around 10, this is much better than bolometers, which are used right now to measure the terahertz signal amplitude. We'll also see that the resonance frequency can be tuned by the changing of a current density. Again, this is not a huge change, but nonetheless, it's continuously tunable. And I saw a new paper submitted to Science where this was fully confirmed experimentally. It will appear probably in a couple of months. The line width is not changing with the current, it's almost constant. And the sensitivity of a detector is actually rather large. The sensitivity of a detector, if a detector has a nano size, is about 1,000 volts per watt, which means millivolts per microwatt, which is comparable to the best Schottky diodes or best GaN diodes used, semiconductor diodes. And diodes are not frequency selective. It is very important to understand that you can get a good receiver in the case when the signal is polarized, circularly polarized, and you will need to construct the antenna in a specific way to get the signal to get the response if the signal is linearly polarized. And the calculations show that for linearly polarized signal, if you are not using the external bias magnetic field, you will not be able to receive anything in the uniaxial antiferromagnet. And you will need a bi-axial antiferromagnet if you want to receive linearly polarized signals. Circularly polarized signals can be easily received with a good sensitivity. So the intermediate conclusion is that if you want to have a receiver which will work with signals of any polarization, you need to use bi-axial antiferromagnetic crystals, and you will increase the sensitivity of a detector if you apply the external bias field. What you can do also to change frequency is to put the antiferromagnet in contact with piezoelectric. In that case, by applying voltage, electric voltage to piezoelectric, you can change anisotropy in the antiferromagnet, and you can change the frequency of an antiferromagnetic resonance. And it can be shown that this magnetostriction is different for different crystals. For example, in nickel oxide, it is the coefficient of tuning in 1.6 10 to the minus 2 kilovolts per centimeter, while in the hematite, it almost 2 orders of magnitude larger. And you can extract the signal either by inverse pinhole effect or using the antiferromagnetic tunnel junction, which recently has been demonstrated experimentally. So my final conclusion is that we demonstrated theoretically that antiferromagnets can be used as active elements in resonant generation and resonant detection of terahertz signals. The sensitivity is comparable to the sensitivity of modern Schottky diodes, and the effect can be observed experimentally, and this is a challenge to the experimentalists who are sitting in this audience and in general. Thank you very much.
Questions?
So thank you for a very interesting talk. So actually I have a question which you didn't cover so much in your talk regarding the generation of terahertz radiation. So it's correct so that there is a terahertz gap where generation of terahertz waves is difficult. Nowadays it's actually not a big deal. So the major issue is that the power of the generated microwave. And can you comment how powerful is your proposed source of the antiferromagnetic radiation?
Well, it's a good question. The power, if we are talking about antiferromagnetic device of this kind, the power is determined by two things. By the, I'm sorry, I did something wrong. Just hold on. Yeah, the power is determined by the bias current and by the volume of antiferromagnet. If I increase the volume of the antiferromagnet, I will have higher threshold of excitation. So I will talk about the values of amplitude of the electric field amplitude. About well, I would say powers in microwatts.
How much?
Microwatts.
How much? Microwatts?
Microwatt, maybe.
Okay, but it's not much.
So
it would be possible to have milliwatts. Would it be possible to achieve milliwatt?
I doubt it. Yeah, it's strongly doubted.
Okay.
So microwatts, tunable frequency with microwatts will be a good success.
Okay, very good. Thank you.
More questions? I have a curiosity.
Yeah. Vincent want to ask me something.
In your final slide, you say that to increase the sensitivity, you can include or insert a magnetic tunnel junction. But then, if I'm not wrong, you have like platinum as a second electrode. So how? I don't.
With sensitivity as in a detector, you see the sensitivity depend. Sensitivity. We assumed that the thickness of antiferromagnet is rather small. It's the thickness of a layer is 30, 40 nanometers, not more than that. In that case, you can get the sensitivity which is good, which is comparable to the sensitivity of GaN diodes or Schottky diodes. So there are no miracles here. Because if you will reduce the volume, you will increase the influence of the noise. And signal to noise should be at least higher than 5. So you can't get, without cooling, the sensitivity higher than, say, several millivolts per microwatt.
My curiosity was answered thanks to the question of Sam, because I was wondering how thick has to be a value, but you answered.
Yeah. I would like to stress one thing. In contrast with many other projects to generate and receive, we are talking only about generators and receivers which can be continuously tuned. Because it's absolutely no problem to generate terahertz when you, say, have a piece of antiferromagnet and you put an optical femtosecond pulse on it. You will generate continuum. This continuum of frequency will contain terahertz. But how to extract these terahertz, how to select them? You will need a resonant receiver like what I'm suggesting. or something like that. So it's no problem to generate continuum of frequencies containing terahertz. It's difficult to generate quasi-monochromatic signal in a terahertz frequency range which can be continuously tuned. The same is about the receivers. Bolometers work pretty well, diodes work pretty well, but they are not frequency selective.
Okay, you can say it again, the speaker.
Thank you.